morning everyone. So, we are discussing about the natural or free convection, and we have seen that how the heat transfer coefficient will be calculated if there is a vertical plate and you will be having a stationary air or atmosphere that will be surrounding around it. Okay. So, how to calculate the heat transfer coefficient and how to utilize that heat transfer coefficient to estimate how much heat has been transferred by the free convection mode. So, now under different situation, whether it is a vertical plate or horizontal plate, whether it is a flat plate or a cylinder or a sphere, the heat transfer coefficient for natural convection will change. So, there are different correlations available for estimation of heat transfer coefficients under these situations, like flow over a plate, horizontal, vertical, cylinder, sphere, etc. Now, we will be looking into in detail those correlations and how to utilize those correlations to estimate the heat transfer coefficient. Once you estimate the heat transfer coefficient, you can calculate how much heat has been transferred due to free convection. Correlation for Nusselt number. For a vertical plate and uniform wall temperature, your length average Nusselt number is represented in this form: C times RAL. RA is basically Rayleigh number raised to the power n. Now, this is related to Grashof number. This is defined as Grashof times Prandtl number. Its expression is G beta Ts minus T infinity L cube by nu alpha. So, basically it depends on the thermophysical properties, dimension, G and temperature difference. Now, all the properties are evaluated at the film temperature. That film temperature is basically the arithmetic average of bulk temperature and wall temperature. Now, for different regimes of Rayleigh number, there is a product of Grashof and Prandtl number, the constants, empirical constants C and N will vary. C will assume a value 0.59 and N equal to 1 by 4 for Rayleigh number less than 10 to the power 9. Okay. C is equal to 0.1, N equal to 1/3 for Grashof Prandtl greater than 10 to the power 9. So, there are various correlations available for estimation of average heat transfer coefficient depending on variation of range of the Rayleigh number that you can have. Now, for entire range, there is one more general correlation is available for entire range of Rayleigh number. The Nusselt number correlation will take this form: 0.0825 plus 0.387 RAL raised to the power 1/6 divided by 1 plus 0.492 by Prandtl raised to the power 9 by 16 whole raised to the power 8 by 27 square. It is a complicated one, but this kind of correlation can be fitted to all the data that you can have for Rayleigh number greater than 10 to the power 9 and less than 10 to the power 9. So, these in one correlation you can cover full range of Rayleigh number that you can have. That goes for the vertical plate. For long horizontal cylinder uniform temperature, the diameter averaged Nusselt number, that is defined as HD HL bar HD bar by K, in the same form 0.6 plus 0.387 Rayleigh based on D raised to the power 1 upon 6, 1 plus 0.559 divided by Prandtl raised to the power 9 by 16 whole raised to the power 8 by 27 square. Okay. So, in most of the free convection calculation you will be having various correlations to estimate the Nusselt number. Now, for sphere, you will be having 2 plus, and I think we had previously described why 2 is coming, Rayleigh number raised to the power 1 by 4, 1 plus 0.469 by Prandtl raised to the power 9 by 16 to 4 by 9. Okay. Now, all these correlations are for uniform wall temperature. Constant wall temperature condition, CWT. Okay. Now, the correlation will take a different form if you have constant wall flux or CHF type of condition. So, in fact, all these correlations are available in the book of Enclosure and Dewitt and Wojcicki or any standard textbook of heat transfer. So, we would like to emphasize that how to use these heat transfer correlations and how the properties will be evaluated and how they will be applicable to a particular problem. Okay. For uniform wall heat flux, the correlation will take the different form. Let us first consider the vertical plate constant heat flux condition. Okay. The local, in this case, in case of uniform wall heat flux, the local Nusselt number is defined at any x location from the leading edge. Grashof number based on length x, Prandtl raised to the power 1 by 5 for local Rayleigh number or Grashof times Prandtl lying between 10 to the 5 and 10 to the power 11. Okay. And this will take a different form slightly, 0.568 Prandtl raised to the power 0.22 for the higher range of local Rayleigh number. Okay. Now, this GRX star is known as the modified Grashof number. And it is defined as GRX multiplied by nu x. This is the Nusselt number, local Nusselt number, and it is defined in this way: G beta. You just write down the expression, then it will be clear. T infinity x cube by nu square QW x Ts minus T infinity. Now, Nusselt number will be defined in this case based on the heat flux. Okay. Because you do not know the and what about this Ts, because you do not know the Ts. So, what will you do? So, anyway, just think about it, we will come to it later on. G beta QW. In this definition it is cancelling, because you do not know the Ts. So, you cannot calculate the Grashof number itself. So, in this way, in this definition, in the modified Grashof number, you define it such that unknown quantity will be cancelled out. But what I would like to tell you later on, that I will come to it. Okay. Now it is cancelling for this definition. In the same way, the in case of the way you have defined the Grashof number initially, you multiply Reynolds number square, the dimensional system that is appearing in your energy equation, because the reference velocity is unknown to you. Okay. So, since it is a case of constant heat flux, you know this QW, and you can calculate this modified Grashof number, okay, from the properties and whatever the values there, those are specified to you, and you can calculate the local Nusselt number. And local Nusselt number is defined based on the length x starting from the leading edge.
What is K here? Sir, NU you have written HX only, HD by K.
No, this NUX is basically based on the distance x from the leading edge, vertical plate.
So you have left an K.
I think we have left a K there, right? There will be K here. Okay. So, this is the definition of NUX. This K was missing anyway, that you check. And QW is constant heat flux at the wall. Okay. And once you get the local Nusselt number, you can find out the length average Nusselt number by doing an integration over the length. Okay. Average Nusselt number is 1.25 NUX evaluated at x equal to L. It is presented in this form. You can once you know the expression for local Nusselt number as a function of x, okay, you can integrate it out over the length and can find out, and is expressed as 1.25 Nusselt number x evaluated at L, x at L. Okay. Ten to the power 11 and 10 to the power 5, and it will be taking this form NUX x equal to L for 10 to the power 13, 10 to the power 16. Okay. Now, physical properties. Evaluated at film temperature. Where is the TF? TF equal to T wall plus T infinity by 2. Now, how this film temperature, that was my point, how this film temperature will be estimated if you do not know the wall temperature, because it is a constant wall flux condition. So, you have to basically assume a value first, calculate the Nusselt number, and find out TF, evaluate the properties, and recalculate, go on iterating like the previous ones we have done. Okay. And in fact, in 1 or 2 iterations the whole answer will be converged. Okay. In the next case, we will be taking free convection on horizontal plate. Now, this average Nusselt number will depend how whether the convection is occurring in the in the top surface or on the bottom surface, okay, or in both the surfaces. So it will depend on that. Basically, it depends on surface facing up or down. Okay. Now, you remember one thing, for the case of vertical plate, we are estimating, say let us take it a case of constant wall temperature condition. We are estimating the heat transfer coefficient to estimate how much heat has been transferred due to free convection, okay, and we are estimating heat transfer coefficient here. This is only true if the other surface is insulated. If it is not, the same phenomena will be occurring on the other side, and there will be the surface area will be doubled, because the calculation will remain the same. H will be remaining some with respect to this surface or the rear surface, only the area will be doubled. So in the case of horizontal plate, it depends on surface facing up and down, up or down. Okay. Now for uniform wall temperature, the average Nusselt number C, this m, the subscript m stands for the mean, okay, mean Nusselt number, or you can put a bar over it, Grashof Prandtl raised to the power n, where this is basically h bar L over k, and Grashof based on length L, g beta Tw minus T infinity L cube by nu square. Again, the unknown temperature, this is not based on the modified Grashof number, this is based on the Grashof number. So this is unknown, so again it has to be an iterative solution. Now the values of constants C and N, they will be depending on the orientation of plate, and range of Rayleigh number. Okay, that is the that is the product of Grashof and Prandtl number. So I have some values. Hot surface facing up and cold one down. These range from 10 to the power 5 to 10 to the power 7, then these values are 0.54 and 1 by n is 1 by 4. For the range, higher range 2 to the 10 to the power 7 to 3 into 10 to the power 10, these values are 0.14 and this is 0.33. Okay. Hot surface facing down or cold one is up, three into 10 to the power 5 to 3 into 10 to the power 10, full range roughly 0.27 and 1 by 4. Okay. Now for uniform wall heat flux, condition, horizontal plate with the heated surface facing up. Some other correlations are also available. Average Nusselt number is 0.13, Grashof-Prandtl raised to the power 1 upon 3 for Grashof-Prandtl less than 2 into 10 to the power 8, and this will be 0.16 Grashof-Prandtl raised to the power 1 upon 3 for 5 into 10 to the power 8, 10 to the power 11. Okay. So, in fact, there are so many correlations are available. In fact, in the book of Holman or in Enclosure and Dewitt, you will be getting host of correlations available for free convection for different situations, whether it is a horizontal plate, vertical plate, constant wall flux condition, constant wall temperature condition, horizontal cylinder, vertical cylinder, sphere, etc. Okay. Which one? This one? 5 into 10 to the 8, in the range of 5 into 10 to the 8 to 10 to the 11. Okay. So what you have to do for a particular problem, you have to identify what is the condition, orientation of plate, etc., geometry, or then you have to calculate these values. Okay, like you have calculated Reynolds number to find out whether the flow is laminar or turbulent. Similarly, for this case, you have to calculate this Grashof and Prandtl product. This is known as the Rayleigh number, and depending on this value, you have to select a proper correlation with a proper exponent, etc., to find out the heat transfer coefficient and ultimately the how much heat has been transferred by free convection.
So here from 2 to 5 into 10 there is no correlation.
That is not available. So in that case, you can use any one of them. In fact, you will see the coefficients are quite close, right? So all these are based on experimental results, and then put into correlation form. For horizontal plate with heated surface facing up, the correlation will be 0.58 Grashof-Prandtl raised to the power 1 upon 5 for the range. We will be solving couple of problem. So 10 to the power 6 to 10 to the power 11 in this range, where Grashof L is defined as G beta T wall minus T infinity L cube divided by nu square, and nu as h bar L by k equal to QW L TW minus T infinity k.
TW minus T infinity.
Right.
Sir, the previous case is also the same thing.
Which one?
This is facing upwards.
This horizontal plate with heated surface facing up,
The last one
and
That was average. Value bar average.
okay, I think there is something I must have copied it wrong. Okay, all these are correlations, so you have to look into the book and see. It might be facing down in that case. That you have to confirm which one is up, which one is down. The idea remains the same. Now let us solve a couple of problems. You have a vertical plate with L equal to 5 meter high. Here is the height, and width is 1.5 meter. Okay, that is the width of the plate. Now its one surface is insulated. This is the insulation you put. You maintain a constant wall temperature to the surface, to the other surface, and constant wall temperature is 400 Kelvin, and this is exposed to a stationary or a calm atmosphere with T infinity around 300 Kelvin. Okay. Now, we have to calculate the total rate of heat loss from the plate by natural convection. Rate of heat loss by natural convection, that we have to calculate. So, basically since it is wall temperature is known, surrounding temperature is known, you can evaluate the film temperature, evaluate all the properties of the film temperature, calculate, use the proper correlation, calculate the heat transfer coefficient. Now, film temperature is the average of these two temperatures, that is around 350 Kelvin. Okay. Then you have to go to the thermophysical table of thermophysical properties for air, and nu will be 20.75 into 10 to the power minus 6 meter square per second. Prandtl is 0.697, K is 0.03 watt meter degree centigrade, beta is 1 by Tf, that will be 2.86 into 10 to the power minus 3 Kelvin inverse. Now, Grashof at L equal to 5, that is G beta, that means G beta Tw minus T infinity L cube by nu square. Okay. This comes out to be 8.14 into 10 to the power 11. Okay. Then you go back to the definition of correlation of average Nusselt number for the vertical plate, and that will be 0.825 plus 0.387 Grashof Prandtl raised to the 1 upon 6, 1 plus 0.492 by Prandtl raised to the power 9 by 16 whole raised to the power 8 by 27 bracket close square. So, you put all the values and H will be turning out to be 5.5 watt per meter square degree centigrade. Okay. And you can find out the heat transfer rate, that is H times area of heat transfer multiplied by Tw minus T infinity, and it turns out to be around 4.13 kilowatt. So, it is basically the calculation of natural convection is a situation which situation you are having natural convection, and you have to select a proper correlation and estimate heat transfer coefficient and find out the total heat transfer rate. I think there is no complication in these calculations. Okay. Only thing is you have to select a proper correlation, that is all. In the second one is a problem of constant wall flux. You have insulation here in one surface, L, it is a vertical plate, L is 3 meter, W is 1.5 meter, and this surface is receiving solar radiation at a constant rate. Qs is equal to 750 watt per meter square. Okay. And alpha S is the absorptivity of this surface, and that is 0.8. Because this radiation, some of it will be reflected, some of it will be refracted, rest of them will be absorbed, and that means this absorptivity should be multiplied with this Qs, that much amount of heat will be absorbed by the plate. Assuming energy absorbed by the plate is dissipated by free convection to surrounding air, that is stationary surrounding air at atmospheric pressure, and temperature, normal temperature 27 degree centigrade, 300 Kelvin. Okay. We have to calculate roughly the surface temperature, the average surface temperature of the plate. This may be useful, this type of calculation may be useful in case of solar heater, or it's sometimes called flat plate collector. Now, your Ts is unknown, that you are going to find out, right. So, Tf cannot be estimated directly. So, the first step is you assume, either you assume a Ts or you assume a heat transfer coefficient, calculate Ts from there, either way. So, whatever the way you do, it will converge within 2 or 3 iteration. First you assume a H, let us say 6 watt meter square degree centigrade. So, QW is Qs multiplied by alpha s, that is 0.8 into 750, okay. That is 600 watt per meter square. Now, you know QW, you have assumed H, you can find out Ts from the definition of heat transfer coefficient. You have assumed H, you know what is QW, and you can find out TW as 400 Kelvin, okay. And now we can find out what is the film temperature, that is 350 Kelvin. It is all the same, either you assume TW or you assume heat transfer coefficient, okay. Now you are in a position to evaluate the physical properties. Nu is 2.076 10 to the power minus 5 meter square per second, K is 0.03 watt meter degree centigrade, Prandtl is around 0.7, beta is 2.86 into 10 to the minus 3 Kelvin inverse. Now, modified Grashof number at x equal to 3 meter G beta QW x to the power 4 by K nu square, and it will come out to be 1.05 into 10 to the power 14, okay. And Hx will be K by x 0.568 Grashof Prandtl raised to the power 0.22, okay. And it will come out to be at x equal to at the end x equal to 3 meter, at x equal to L, this value will be 6.38 watt meter square degree centigrade at x equal to 3 meter, that means at the end point of the plate, okay. Now, you know you have the heat transfer coefficient, average heat transfer coefficient over the length is 1.136 Hx x evaluated at 3. So, we will be just simply putting this value there. For this length 0 to 3 is 1.136 Hx x equal to L or 3 meter here. So, it comes out to be 7.25 watt meter square degree centigrade, okay. Now, you can calculate what is my wall temperature. What is wall temperature? That is T infinity plus Q wall by this average heat transfer coefficient, okay. It comes out to be 382 0.8 Kelvin. And when we assumed the value of H, we are getting TW as 400 Kelvin. That means we are very close, or you can further improve this closeness. Okay. So iterate till convergence of your desired degree. So that is how you tackle a problem of constant wall flux. Now till now whatever we have done, we have looked into how free convection correlations will be developed and can be used for calculation of heat transfer if it is semi-infinite plane, it is open to one end. Now you can have free convection in an enclosure. The typical example is a flat plate collector, where you have two plates and in between there will be some air or some there are some top plates will be placed one above the another with a gap in a solar panel, all those flat plate collectors. So there might be, and that air that is entrapped between the two plates, they will be stationary and there will be recirculation, there may be recirculation and causing natural convections. So natural convections in enclosure in any enclosed space or in a conduit may be of importance in chemical engineering. So we have to look into various correlations for free convection in a closed conduit or enclosed space. Closed conduit. Okay. Now the examples are free convection in wall cavity, between window glazing in the annulus of concentric cylinders, spheres, flat plate collector, etc. Now, if you ever see the window of a AC coach, you will be finding there are two glass plates on the inner side and one on the outer side, and in between there is an enclosed space, right. So, you may be able to you may be interested to calculate the free convection effects in that space. That will be one of the examples that can be found out in everyday application. There are two plates separated by a distance delta. Top plate is at temperature T1, bottom plate at temperature T2. Now, if T1 is greater than T2, then will there be any heat transfer? There will be heat transfer because there will be temperature gradient, but there will be no natural convection, there will be conduction only. Heat transfer by conduction. Okay. That means A times K Th or T hot minus T cold divided by delta, that will be total amount of heat that has been transferred, H times A times Th minus Tc, and in this case your Nusselt number will be exactly equal to 1. It is a case of conduction only, and if you impose the amount of heat that has been transferred in the definition of Nusselt number, your Nusselt number will turn out to be 1. Now, if T2 is greater than T1 and if the difference of T2 and T1 is such that your buoyant force overcomes the viscous force, you can have natural convection. Occurs. Okay. Now, even here, if T2 minus T1 is small, there may not be natural convection, okay, provided the buoyant force is less than the viscous force. no natural convection. That means there must be some critical Rayleigh number or product of Grashof and Prandtl beyond which there will be occurrence of natural convection, and this critical Rayleigh number Grashof number based on the delta, the spacing between the two plates, G beta T hot minus T cold delta cube divided by nu square times Prandtl, right, and this critical value is 1708. In fact, you can theoretically prove that this critical Reynolds number is 1708 by an instability analysis of your governing equation. What do? You write down your governing equation and put and impose an instability, okay, by putting a wave type of function. Okay. Then you do the analysis. It is known as Orr-Sommerfeld analysis, that we have not done, but it is a material of any advanced fluid mechanics course. Even you can the same way, it is called normal mode analysis. Okay. So, in the same way you can estimate the transition of laminar to the turbulent flow. Okay, and you can find out the critical Reynolds number. In a similar way, you can find out the critical Rayleigh number here, where there will be occurrence of natural convection. Now, the enclosed spaces that we are considering, one is horizontal surface, it may be a horizontal surface, okay. This is delta, this is T hot, this surface is top surface is T cold, and the separation between the two surfaces is delta. You can have vertical surface, this is T hot, T cold, this separation is delta, this height is h. Okay. You can have inclined surface. So, we will be considering the natural convection within the space, within this space, okay, of this enclosed this thing. This angle is phi, this surface is hot, this surface is cold, and this separation is delta. This separation is important in all the case, because all your Nusselt number etc., will be based on this characteristic distance delta. Now, again there are empirical correlations available for these cases. Nusselt number based on delta is h delta by k c times Rayleigh based on delta raised to the power n h by delta raised to the power m. Okay. And the number R A delta is based on, is defined as Grashof times Prandtl, and it is G beta T hot minus T cold delta cube by nu square times Prandtl. Okay. Delta is the thickness between the fluid layers, between the two surfaces basically. Now, in an annulus, this is nothing but outer diameter minus inner diameter divided by 2. In a plate, it is the separation between the two surfaces. H is the height of the fluid layer, and all the properties are evaluated at the average temperature. All thermophysical properties average temperature of the two surfaces. Now, Q is total heat transfer that is occurring per unit time is A m times H m, that is the heat transfer coefficient, multiplied by the Th minus Tc. Okay. Am is mean area depending on geometry. Okay. Now, for the plane layer, that means if it is heat transfer between two horizontal plates, then area will be area of the plate, that is the heat transfer area. If it is cylindrical annulus, you can calculate the area, and for sphere also some average area will be there. Okay. Plane layer means it's basically enclosed space is basically within two rectangle surfaces. That is the oval area. Cylindrical annulus A0 minus AI divided by ln A0 by AI, some kind of area average, and for spherical annulus your aim will be a geometric mean of outer area and inner area, some kind of average area. Now, for vertical plates, it is not a plate, they are called its layer. Basically, you have a box vertically placed within which you would like to calculate the heat transfer coefficient. Vertical layer and vertical cylindrical annulus, that is the enclosed space we are talking about. Either it is an annulus or it is a space between the two plates. For the gas, Rayleigh number less than 2000, C is equal to 1, N equal to 0, M equal to 0 in your previous calculations. For Rayleigh number within the range of 2000 to 2 into 10 to the power 5, your C will assume a value 0.197, N equal to 1 by 4, M equal to minus 1 by 9. For Rayleigh number in the range of 2 into 10 to the power 5 to 10 to the power 7, value of C will be 0.073, N equal to 1 upon 3, M equal to minus 1 over 9. Okay. Similarly, for the liquids you will be having several correlations. Okay. Now, these are for the vertical plates or vertical surface, and for the horizontal surface layers or cylindrical annulus, you will be again a host of correlations, and depending on the values of Rayleigh number you will be getting different values of these empirical coefficients. Okay. Now, all these are listed in your book in the tables. Okay. So, I have correlations for cylindrical annulus, spherical annulus. So, the idea remains the same. Now, there will be one last thing about this free convection. There are some recent development of more accurate coefficients of more accurate correlation available for free convection in enclosure. They are like this. For vertical layers or vertical surface, you have to calculate Nusselt number based on 3 Nusselt number, and you have to select the maximum of the 3 NU1, NU2, NU3. Okay. Now, what is NU1? It's there is a relationship for that 0.0605 Rayleigh raised to the 1 upon 3, NU2 1 plus 0.104 Rayleigh raised to the power 0.293, 1 plus 6310 Rayleigh raised to the 1.36 whole cube raised to the power 1 upon 3. Okay, these are some relations, and NU3 is 0.242 Rayleigh by A raised to the 0.272, where A is H by delta. Okay. Now, you have to select the maximum of these 3. Okay. Now, these correlations are this type of approach is supposed to be better than the previous one, where we had C, N and M. Okay. Then for inclined layers, again you will be having correlations. There is nothing. You have to compute. If there are 3 correlations available, you have to compute NU1, NU2, NU3 and select the maximum of the 3. And it somehow turned out to be better heat transfer coefficient compared to the other one, where you had C and M and N. Now, for inclined layers, there are correlations available for between 60 degree and 90 degree. 90 degree means it is vertical, okay, and 60 degree, and there are correlations available for phi lying between 0 degree and 60 degree. Okay. Again, NU60 is given as maximum of the 60 degree, NU1 and NU2. For NU1 you will be having one correlation, for NU2 you will be having one more correlation, then you will be calculating NU60. Okay. And for any phi, and NU90 is basically the vertical layers that you know. And suppose you will be having something between the inclination 70 degree, 75 degree, 80 degree, you do by linear interpolation. Okay. For any phi lying between 60 degree and 90 degree, is simply given by 90 degree minus phi NU60 plus phi minus 60 degree NU90. NU90 is basically for the vertical layers, and NU60 will be calculated from this. Okay. And again you will be having similar relations for the inclined layer less than 0 to 60. I am not writing those things in detail. And for horizontal cylindrical annulus and spherical annulus, you will be selecting. There will be again some correlations available which will be which are supposed to be better lot compared to the other one. Now, if you compute the heat transfer coefficient using this relations and the other one, the difference will be in the order of 10 to 12%, maximum 15 to 20%, not more than that. So, anyone can be used for for a rough estimation. Okay. Thank you. So, we end the free convection here. So, free convection is full of correlations basically, and you have to select a proper correlation to calculate the heat transfer coefficient and ultimately the heat transfer rate. Thank you.